Hi. Today we just continue what we started regarding projectile motion and circular motion. We solved some problems on chapter 4, from the review problems. So if you have the review problems paper ready, if you look at question number 17, question number 17, okay? And we'll show it on the camera, 17, question 17. The question says, a rifle is aimed horizontally towards the center of a target 100 meters away. But the bullet strikes 10 centimeters below the center. Calculate the velocity of the bullet just as it emerges from the rifle. As it emerges from the rifle. Okay, so I'll just do a sketch here on the board for this question 17. A rifle, fire a bullet horizontally, aiming at the center to hit this target. Okay? Now, the distance between the rifle and the target is given. How much is it? No, horizontally. Horizontally 100 meters, yes. And remember, if you fire horizontally, aiming at this point, you will not hit this point because of gravity. So you have a projectile motion. So you will hit below. The question says you hit 10 centimeters below. What is the question? Calculate the velocity. This is chapter 4. And motion in 2 and 3 dimensions. So we want the velocity as it emerges from the rifle. Which velocity is this? This is initial, and here you have final. Which one? Initial here, firing, yeah? Initial is V naught. We need V naught, yeah? All right. Now, what type of projectile is this? Remember the 4 types of projectile? Symmetric. And 3 non-symmetric, yes? The 3 non-symmetric, above horizon, horizontally or below? So the angle of firing here? Now, any projectile, we said, can be solved by 4 equations. 3 vertical, 1 horizontal, and 1 statement. I'll list them here. X, motion, displacement, V naught cosine theta naught multiplied by t. And we have final velocity in x equal initial velocity in x. Remember, this means V naught x. And acceleration in x is 0. No acceleration in x. Vertically, we have free falls. Final velocity in y equal initial velocity in y, which is V naught sine theta naught minus gt. Final velocity in y square, initial velocity in y square minus 2g displacement vertical, and delta y, initial velocity in y multiplied by the time minus half gt square. For all projectile motion, you have these equations, yes? On top of those, you have 2 more if you have a symmetric, yes? The h max and range. We don't need them here. Now, you need V naught, yeah? Now, V naught, you can find it in x and you can find it in y, because this is V naught, V naught, V naught, V naught, V naught, yeah? Okay. But in this question, how much is theta naught?
0.
So if I put theta naught 0 here, the V naught will disappear. So you cannot answer the question, yeah? Disappear. So you have to work this side. Okay. This is V naught. To find V naught, you need delta x and time, yeah? Okay. Delta x horizontally given, yeah? How much is it? 100. Unknown? 1. Time? Unknown. Fine. When the time is unknown, what you do? You go vertically, find the time, and then use it horizontally, yeah? So what we do here, we say delta x between 0.1 and 0.2 equal V naught cosine theta naught t from 1 to 2, and this is delta x from 1 to 2. How much is delta x? 100. V naught unknown. Cosine theta naught 1, because theta naught is 0. Cosine 0 is 1. And the time unknown, 1 to 2. So here you have two unknown. You can't solve. You go and find the time vertically. Now, you have to stick to the same range. The range you're doing between 1 and? So now vertically between 1 and 2, what do you know?
10 centimeters. Delta y.
You have delta y. How much is it?
Negative 10.
Minus. Because initially here, finally below, delta y is negative. And change the centimeters to meters. Divide by 100. So it becomes point. So this is 0.1 meter. Okay, divided by 100. Right, so if I choose, first one has time, but it has Vy. What is Vy? Here, Vy here, unknown. Vy2, unknown. So I cannot use the first equation. And anyway, it's not useful because what you want. So go to the last one. It has time and vertical displacement. How much is delta y between 1 and 2? Okay, 1 to 2, V naught sine theta naught t from 1 to 2 minus half gt squared from 1 to 2. How much is this?
0.
0. Why? Because theta, 0. Sine 0, 0. So you'll have minus. I write 0 so you remember. Minus half 9.8. And how much is delta y? Minus 0.1 meter. Why minus? Because initially this is y1. Finally y2. You're going towards y2 down. Minus. Minus with minus. Do the calculation. You find what? Once you find t, substitute here. How much is the time? 0.14 second. You put here, back, 100, V naught multiply 0.14, you find V naught, which is 100, 14, yeah? We finished the question or not? Finished, yeah? Okay, now, what are the other questions you can answer here? Find what? When it hits the target, what is the velocity, which means V2, vector. When you say velocity, you mean the vector. What else you can say? What's the speed when it hits, which means the magnitude of V2. To find V2, what do you need? Vy2, Vx at 2, yeah? Right, remember in projectile, Vx doesn't change. Vx same as V naught x. And what is V naught x here? You found it. It's V naught, yeah? Okay, find this one. And then V2 as a speed will equal to root Vx square plus, this is a speed at 2. Just substitute, yeah? Vx is this. And this is 1, and V naught, you found it. Okay? And Vy, you have to calculate it. If I use this equation for Vy, this is 0. And the time, 0.14. You find Vy and substitute, yeah? Anything else you can calculate? That's it, yeah? Remember, you have 4. Initial velocity, final velocity, displacement, and time, because g is known. These 4. If you know 2, you can find the other 2, yeah? But in total, 4. So this was question 17. Now let's take another question when it's above horizon. Question 21. Question 21. A rock is thrown from the edge of a top of a 100-meter tall building at some unknown angle. So the firing angle is unknown. Above horizon. It's not below or horizontal, above. The rock strikes the ground a horizontal distance of 160 meters from the base of the building. 5 seconds later, after being thrown, determine the speed. Now, when you say determine the speed, remember you have 2 speeds. You have speed, initial speed. We have to complete the sentence. Determine the speed with which the rock was thrown. Initial speed, V naught. Here, we need V naught magnitude, not V naught vector. And remember, if you know the vector, you know the magnitude. Okay, so I'll do the diagram for you, which here. So this is the diagram. This is the ground. This is the building. And the height of the building, h, 100 meters. You fire above horizon with V naught. And this is theta naught. It goes up and then back to the ground. And it hits the ground at a horizontal distance of 160 meters. What else is known from the question? The time. If I say this is 0.1, this is 0.2, 1 to 2, 5 seconds. Anything else is known? Nothing, yeah? Okay. Again, the table. Horizontally, delta x and Vx equal V naught x. Vertically, the free fall, the 3. What's the question? Find V naught. So V naught unknown. How we start? Again, V naught, you can find it in x and y here. Suppose you go for this one. Horizontally. Delta x, V naught, cosine theta naught, t. Between 1 and 2. How much is delta x? 160. V naught, unknown. Theta naught, 2 unknowns. Time, unknown. Given? Given. Good. Given. Good. So now I can say horizontally, delta x, V naught, cosine theta naught, t, from 1 to 2. Delta x, 160. V naught unknown. Cosine theta unknown. But the time is 5. In this equation, how many unknowns? 2. Oh, okay. Actually, you can make those 2 1 unknown. Why? Because V naught, cosine theta naught is V naught x. Where is V naught x here? It means if this is V naught, this is V naught x. The component horizontal, V naught x. And this is equal to V naught cosine theta. So think of this as V naught x only. And then 160 over 5. It gives you V naught x. We didn't answer the question yet. We found the component V naught cosine theta, both. But we need V naught only, yes? Okay. Now, on x, I can't do anything else because I have one equation. I finished. Now let's go. Vy. Remember, Vy or y motion, you have V naught in the first equation, second, third as well, yes? Vertically, between 1 and 2, what do you know? What else? And time. So which equation is useful? So I'll take this one vertically. Again, it's the same here, but there is no 0 here. So delta y from 1 to 2, V naught sine theta naught t minus half gt square 1 to 2, 1 to 2. Delta y between 1 and 2?
It's minus 100.
Minus 100, well done. Minus 100. From this point down. Now V naught unknown. Theta naught again. What does V naught sine theta naught mean? V naught y here. So just put it as V naught y. Time 5. This is 4.9. 5 square, yeah? You'll solve it, what you'll find? V naught y. So now, you have V naught x and you want V naught. V naught is a vector, yeah? It has two components. So if you know the component, can't you find the vector? How? Square root of both components. So V naught vector as a value is equal to V naught x square plus, and both are known. You found here and here. Substitute. So this one goes here, and this one will go here. You find V naught. What is the other question you can answer? Always create questions. What else you can calculate in this question? Maximum height. Okay, good. Maximum height, she said. Be careful here. When you say maximum height, here is non-symmetric, yes? But you mean here, not the maximum height in symmetric. You mean the from this point to the ground, yeah? Okay. If you want to find this h, I will not call it maximum, I call it h, from here to there. What you have to do?
You find the maximum height and then plus 100.
You have to do calculations between point 1 and which point? 2. No, not 2. This is 2. This point. Shall we call it 3? Okay. Now between 1 and 3. Of course, now you know V naught, yes? You know V naught or not? What else? Do you know theta naught? No. But can you calculate it now?
Yes.
How?
V naught x equal V naught y or V naught y.
There are many ways. If you go back here, delta x is known. This one found, t known. You find? But remember, the easy way is that this is a triangle, yeah? You have V naught x, V naught y, and this is theta naught. So use tan theta naught equal V naught y over V naught and find theta naught, yeah? So you can find theta naught by tan. Okay, now, what do I know at 3? Vy here at 3 is 0. But Vx equal, same, this one. Doesn't change. Right, now what you have to do between 1 and 3? Vertical, do you do vertical or horizontal? Which one is easy?
Vertical.
Why? Because you know Vy here? 0. Vertical. So if I apply maybe equation 1, 2, or 3, between 1 and 3, what do I put for Vy? 0. When you put Vy 0, you are calculating between 1 and 3. So if I put this 0, this is known, I'll find time between 1 and 3. One by one. As if I don't know what to do. I just go through all three. So if I use this one, this is 0. It gives me the time between 1 and 3. But remember, you need h, yes? Let's go for this one. When I put this one 0, this is known. What can I calculate? Between? But this is not h. So when I do calculation between 1 and 3, and I find delta y from 1 to 3, I add it to the height of the building. It gives me h. Let's call this one h1 because this will be h2, yeah? So what you say from here to there is h1, yeah?
But don't you think that's root value of delta y?
Yeah, but anyway, this will come out positive because it's above. Okay? That's it. So find delta y between 1 and 3 and add it to the height of the building. What can you ask me about this point?
Final velocity.
Speed when it hits the ground. What do you need? Vx and? So you find v, eh? Vx doesn't change, v not x. Vy, you have to find it. Between 2. So use vertically between 1 and 2 and find the time. Next question, 23. 23. This is another example of firing below horizon. Below horizon. 23 says you toss a ball from your window 8 meters above the ground. So like now we are in this classroom. Let's say this is 8 meters from the ground. You toss, you throw a ball. When the ball leaves your hand, it is moving. That's when it was in your hand. It's moving at 10 meters per second at an angle of 20 degrees below the horizontal. This is below. How far? Horizontally. Horizontally. Delta x. From your window, will the ball hit the ground? How far from the window? Ignore air resistance. Of course, we always ignore air resistance, yeah? 20 degrees. So I'll do a sketch here for the question. There is a building, and probably you are here maybe, 8 meters above the ground. This is your window. You toss, you throw. But which way you throw it? Above horizon, horizontal or below? So this is horizon. Below. What's the angle? 20 degrees. And the firing angle, speed? 10 meters per second. Of course, it will not go straight, go as a projectile, hits the ground here. What's the question? Find the delta x. Anything else is given? No, okay. The table in front of you. You need delta x, so you have to work on x. If you need delta x, what do you need? Given? Theta naught? How much is theta naught? It's not 30. When you fire below horizon, this is not theta naught. Theta naught here is 360 minus. Okay? So whenever you fire below horizon, change the angle. 360 minus. All right?
Can we use minus 20?
You can, but it's better because do it this way, the calculator, your calculation will be right, yeah? Okay? You don't have to worry about changing the value, putting your own minus. The answer will come up by itself. So this is known, theta known, time unknown. Same problem like before. When you don't have time, you go and seek help from the vertical. Okay, now think vertical between 1 and 2. Point 1. Delta y is given minus 8. Anything else is given? The angle is given. So which equation will help? Last one. Here you put minus 8, 10, sine 340, t unknown, minus 4.9, t squared. This is a quadratic equation. Solve it. You have two answers. One of them is negative. Why here you don't have both positive? Look, this is symmetric or non-symmetric? In non-symmetric, you don't have two positive. Okay, one negative, one. Of course, you ignore the negative, you get the positive. Once you find the time, substitute here, you find delta x. Same old story. Now, question 20, maybe I didn't mark it. It's the same page up. We're just going back, 20. I just want to give an idea here about question 20. An arrow is shot with a velocity of 40 meters per second at an angle of 30 degrees above the horizontal. The arrow is initially 2 meters above the ground and 20 meters away from the wall, from a wall. There is a wall, as shown in the figure. The question is, at what height above the ground does it hit the wall? At what height it hits? Part A. Part A is not that difficult. Part B is interesting. Part B says, is it still going up just before it hits the wall, or is it already on its way down? Prove. It's not just you say it. You have to prove it mathematically. Okay? So I'll just do a sketch for you here. This is a wall, and here at a height of 2 meters, you shoot an arrow at an angle above horizon, 30 degrees. And initial speed, 40 meters per second. So what happens? It will not go straight. Projectile. It hits the wall here. What's the question? At what height above the ground does it hit the wall? At what height? This is at what height. But measured from where? From the ground, says. So we need this h. All right. Right. What type of projectile is this? Non-symmetric. Above horizon. Okay? You have the table. If you want anything at the wall, it means you have to do calculations between start and at the wall, yeah? The distance between the wall and the point is giving. How much is it? I put it down there. 20 meters, yeah? From here to there. Delta x, yeah? So, from 1 to 2, how much is delta x? So if I work horizontally, I put it 20. V naught? Theta naught? What can we calculate? Time when it hits the wall. Okay? So find the time when it hits the wall. Delta x, V naught, cosine theta naught, t. Here 20, 40, cosine 30, t. Okay, find the time. So one of you can do the time. 0.5. That's 8 seconds. This is time from 1 to 2, yeah? Remember, you don't need the time. You need the height. But can you find the height to start with? Can you work here without knowing the time? No. That's why we found the time. So now this time we take the time from x to
Y.
now from 1 to 2. I have delta y here. Of course, this will be much better because I have the time, yeah? So from 1 to 2, delta y from 1 to 2, v naught sine theta naught t 1 to 2 minus half g t square 1 to 2. How much is delta y between 1 and 2? Unknown. Is it h?
No.
That's okay. So where is delta y? It means this part. You are not finding h because this is your reference. Initial, final. All right? So now delta y unknown. V naught 40 sine 30 time 0.58 minus 4.9 0.58 square. What we'll find here, delta y from 1 to 9.95. Nearly is 10 meters, yeah? All right, so now what's the answer for the question? So h is delta y plus 2, yeah? You can call this something else, yeah? This 2. Let's call it h1, yeah? And this is h2. So h2 equal delta plus h1. 10 plus 2, 12. All right. This is the first part, A. What is part B? This is part B. Listen, I'll explain this part. Part B says when the arrow hits the wall, was it still going up or it's way down? Now you might think here, by looking at the diagram, you think this is the maximum. No, this is not the maximum. Look, I'll redraw it for you. Imagine there is no wall, and the projectile is doing it. There's no wall. Huh? Where is the maximum? So when it hits the wall here, is it in its way up or down? Up. But do you know this is the scenario here? No. Maybe it's this. This is the max here. So when it hits the wall, where it's going? So the question says, is it this or this? What's the difference between this point and this point? Vy. If it's in its way up, when I draw the velocity, this is v, yeah? So this is Vy positive. And Vx always positive. But here, when it's in way down, this is Vx. So it means find Vy when it hits the wall. And then see, if the Vy sign is positive, it means it's way up. If it's negative, so which equation do you choose? First one has Vy, yes? Between 1 and 2. Known? V naught? Known. Theta naught? Time? We found it, yeah? When it is the wall. You find Vy. Positive, up. Negative, down. Now, let's say one of you chose this equation. This is Vy as well. This is Vy square. So when you take the root, you have plus and? So you don't know which one. So don't choose this one. Because you can't tell. Okay? I want another method to say if it's hitting the wall while it's going up or down, not by Vy. Think of another way. How do you know when it hits the wall it's going up or down? There? No, the angle doesn't. Oh, this is the same angle.
We can find delta y, but after the time of 0.5.
How do you find delta y after? Remember, you have delta y before and after they are equal. So choosing delta y to find the answer is not a good way. Okay, so here she says, I find Vy when Vy is equal to, which means you are looking for the maximum. And then? And you find the time when Vy is 0. Let's give you the time from start to where? Max. And then you compare it.
The original time.
If this time is shorter than that, it means before. If it's more, after. Good. That's how, so you are using the time to judge. Okay? Another way. There are many ways to solve this question. Think horizontally. Delta, how? What do you find in delta x? Delta x is given from here to the wall. What else you have to calculate? She said the time. R. Think of this as symmetric, remember? This is not symmetric, but remember, think of it like up to here, as if there is no wall. You find the range, yes? Which is easy, yeah? Okay, you found the range, then? No, you don't compare the range. You compare it with half of the range. Half of the range. So if delta x is less than half of the range before, if it's more than half of the range, going down. Yeah? That's the other way. Right, let's take more. Let's go to the circular motion now. Yeah? This is enough for projectile. So now we'll take questions on uniform circular motion. Uniform circular, from the section of uniform circular motion. So if you look at the first question 28. Question 28 on page 7. A ball is tied to the end of a cable of a negligible mass. Cable and a mass. The mass of the cable is negligible, very thin, fine. Why we say negligible mass? Because we don't want to include the mass of the cable in the calculation. And circular motion, you need the mass to be away from the center only, nothing in between. No mass in between, no mass distribution, because it becomes a rotational motion. Okay? Now, the ball is a span in a circle. So now the word circle means you have circular motion. With a radius of 2 meters. The radius of circle, 2 meters. Making 7 revolutions every 10 seconds. What is the magnitude of the acceleration of the wall? What's the acceleration of the ball? Okay, now here, of course, here is easy when I say what's the acceleration. You know, I'm talking about centripetal acceleration, radial acceleration. But later on, if I say what's the acceleration, maybe you mix it up with other chapters. Acceleration, yeah? You should know that when we talk about circular motion and we say acceleration, we mean centripetal, yes? Even it's not mentioned. You can add the word centripetal. Okay. Right. Object doing a circular motion at a radius of 2 meters. Now, what does it do, this one? It does 7 revolution every 10 seconds. And what's the question? Find the centripetal acceleration, AC. All right. Right. Now, let me remind you of uniform circular motion. In uniform circular motion, you have 2 equations and 1 conversion factor. What are the two equations? Centripetal acceleration equal v square over r. Remember, this is velocity square becomes speed, yeah? Square over radius. And speed or velocity magnitude, I don't put absolute, but it's okay. It's 2 pi over radius, yeah? And one conversion factor, one revolution is equivalent to 2 pi r. And what's the unit? The unit depends on the unit of radius. Could be meter, kilometer, millimeters, whatever. Thank you. Over capital hour period. Yeah, this is the second one. The speed is 2 pi r over the period, time of one revolution. All right. Now let's go back to this question. You need AC, which means this one, AC. To find AC, you need the velocity and radius. Radius given, but the velocity or the speed not given. This is the equation of speed. You need the radius and period. Period, what is period? Time of one? Okay, now don't grab any time in the question and you think this is the period. No, period means the time of one revolution. What is given here? Whenever you have number of revolutions and times, do a ratio. Now your ratio is two ways. Either you put time over number of revolution, or you put number of revolutions over. Now the first one is useful. When you divide time over number of revolution, what you will find? Second per, which means the period. Time over number of revolutions, what's the unit? Second per one revolution. That's the time of one revolution. But if you do the other way around, if you put number of rev per time, now we don't need this one here. You'll have rev per each second. This is, we call it frequency. We don't need it here. Or angular frequency. No, we need it in chapter 15. Okay, so do this. Of course, if you do this one, what happens? You have to change the rev to what? By using this conversion factor. You can find this. But do it from the beginning. So what is T? Around 10 over? 7. So 10 over 7 is period. Once you find the period, substitute here. And the radius, you find? Once you find V, put it here, you find H. H. You find revolution per second. You have to change it to speed. How? Multiplied by the conversion factor. So put one rev down, 2 pi r, meters or centimeters, depends on, and then cancel them. Next question, 30. Question 30 says, question 30, a satellite orbits the Earth a distance of 1.5 times 10 to the power 7 meters above the planet's surface, and takes 8.65 hours for each revolution about the Earth. So this satellite goes around the Earth. The Earth's radius is 6.38 times 10 to the power 6 meters. That's the radius of Earth. What is the centripetal acceleration of this satellite? What is the centripetal acceleration of the satellite? Okay, now we'll just do a diagram here. Now, in the first question, what did we have? A cable and a mass at the end, and thus circular. And what was in the center? Just a point, yeah? Now, when you talk about planets and satellites, you have big objects, yeah? So like the questions we have the Earth. I can't say the Earth is a point. Okay, Earth is not a point, but this is the center of the Earth. And I have a satellite goes around at a distance, yeah? Where is the satellite? Maybe here in space, yeah? Now here, the satellite, we think of it as a point because nothing is mentioned about the dimensions of the satellite. So we consider it a small point. This is the satellite. Now the satellite goes in circular motion around Earth. Now in circular motion, what do you need? You need radius, yeah? Radius means from the object to the center of the circle. This is the center of Earth is the center of the circle, from here to there. This is R, okay? Now, because you have a planet, either R is given directly from the satellite to the center of the Earth, or no, it's given stages. Usually, when you stand on the surface of Earth, you can measure the height. How high is the satellite? Which means how far is the satellite from the surface of Earth? And this is what is given in the question. From here, from the surface to the satellite. How much is it? 1.5 times 10 to power? Is this the radius? Okay. What I have to add to it? The radius of the Earth. R Earth. And this is given as well. 6.38 times 10 to power? Meters. So what's the radius in this circular motion? H plus RE. This is the idea. Nothing special. So whenever you have satellites and you have radiuses, the R is R of the planet, here is Earth, plus how far it is. H. Now, I think the rest is, you can do it. What do you want? Acceleration of the satellite, yeah? AC. Do you know the radius? Yes. Do you know the speed? Go and calculate the speed. Do you know the radius? Yes. And the period given? It's given in the question. It says it makes one cycle. Each what? 8 point? Hours. This is the period. Time for one cycle. Change it to second. So this is the period. Period is given 3,600 seconds. So change the period to seconds. Put the period here. The radius is given. Find V. Put V here. You find AC. Okay. You should be able to do reverse calculation. Maybe you have AC, and what you need? Period or speed or whatever. Yeah. It's not like you're going. Or maybe you have the number of revolutions per time. And you want to find AC. So if you have number of revolutions per time, change the revolutions to meter per second by using the conversion factor. Next question. 33. Question 33. Question 33 says, if the moon makes a complete circle, look, the moon makes a complete, so what does it mean complete circle? One revolution. Around the Earth in 29 days. So the moon goes around Earth in how many days? This is the lunar month. The lunar month is 29 days, yeah? Approximate here. And the distance, look, the distance between the center of Earth and the center of the moon is 3.8 times 10 to power 8 meters. Find the magnitude of the centripetal acceleration on the moon, which is AC for the moon, yeah? Look here, I'll draw it here. Now this time you have two planets. Earth and the moon, smaller. But the moon goes around, yeah? circular motion. Where is the radius of the circle? From the center of Earth, center of the moon, R. Now, either this is given or you have to calculate it. And this question is given. Says from center to, but maybe other question, we give you the distance from the surface of Earth, surface of the moon. This is like H. And here, radius of the Earth, radius of the, you add all these, it gives you R. Okay? Now, what is known in this question? What's the period? 29 days. So you have to change it to second. If the period is given, the radius is given, you find the speed. Put the speed, you find the acceleration. Now we go to the last question, 37, which is a mathematical question. I will not solve it in details, but I just give you a hint. I want you to practice on this idea. I don't have time to answer outside, because I chose those because I know that they can complete the concepts for you. Anything else? Come and ask me outside the class. 37. An object moves in a circle of a radius capital R. So it goes in a circle, radius R. Capital R, unknown, but R. At a constant speed, so here we have uniform circular, constant speed of it, with a period, capital T. If you want to change only the period, which means you are allowed to change the time for one cycle. In order to do what? Why you want to change the period? In order to cut the object's acceleration in half, which means you want to make the acceleration centripetal half of what you had before. So you change the period, and the purpose to change the acceleration to half, exactly. The new period should be what? These are the options. Should it be the old period, T over 4, which means a quarter of the old? Should it be half T over 2? Should it be T over root of 2? Should it be T multiplied by root of 2? Or should it be 4 times the period? Yeah? These are the choices. Now, let me explain this question, give you a hint about it. And this question is not just in physics. You can have questions similar to this in any branch of science. The strategy of solving these questions are like that. You have to start with the formulas you have. And you use the formula before and after, or formula with subscript number 1, present, and formula subscript number 2, future. Yeah? Or past, present. Or present, future, doesn't matter. So what you have a scenario here. Before and, but the same equation. Here we have circular motion. How many equations do I have in circular motion? 2 only, yes? So it means I use these equations before the change and after the change. What else? You have to know that before and after, what hasn't changed and what has been, and you write them mathematically. Then you can link the 2 equations. Yeah? So now, I say before. I say AC before, number 1. Velocity before, or speed before. Over radius before, R1. He used capital R, but I use small r. What else do I have? Velocity before, 2 pi radius before over the period before, which means original period. Before you do any changes. Now the same 2 equations, write them after with subscript 2. So here you say AC after the changes. Velocity after the changes. Radius after the changes. Speed after. 2 pi. Radius after, period after. Yeah? This is general for any question. What you do next? Now, you read the question and see if there are things hasn't changed. What hasn't changed in the question, before and after? So here you write R1 equal to, which means I can replace them by 1R, okay? Right, what did you change before and after? Acceleration, yeah? Of course, the period I wanted, it will change. So still I have T1 and there is no change in those. There is no link between those two. You have to find the link. But AC, before AC, what does the question say? The AC before the original is what? Twice the new one. Or the new one is half of that. So I'll put it this way. You'll have 2 AC2. All right? Now, the next step is standard. Divide before. It gives you a ratio between before and after. Or if you say after over before. New over old or old over new. In your question, what do you want? The new period, yeah? In terms of the old. The new is here, yeah? 2. So you can divide 2 over or 1 over 2. So anyway, divide these two equations. While you divide, you have ratios, yeah? And these ratios, R1, R2, are the same. You can cancel them, yes? If you see AC1 or AC2, you can replace AC1 by, or this one by half of this. So you have 1 AC, yeah? Put that one there. You simplify it mathematically, you have a relationship between T1 and T2 and see which one is the answer. Yes? This needs a bit of work, mathematics, not much. Okay, this way we finish the chapter. I want to try something today for a change. Let's see if the PowerPoint will show for a while on the... Actually, I will not ignore it because it's not that useful. Okay, chapter 5. The laws of motion. The laws of motion. So far, what we did in the last 4 chapters, we talked about motion in 1 dimension, then motion in 2 and 3 dimensions, and because of that, we needed a chapter on vectors. Motion in 2 dimensions, 3 dimensions, need vectors. So we took a chapter on vectors, motion. But up to now, when we talked about motion, which means when we talked about initial velocity, final velocity, displacement, acceleration, time, all these things, yeah? Did we say why the object moving? Why it's changing direction? Why it's move? Why it's changing speed? Why it's accelerating? Why it's slowing down? Did we ask? No. But we solved the problem, yeah? We found acceleration, time, everything, yeah? Okay, now, when you study motion without looking at the cause of motion, and this is what we did so far, yes? When you don't look at the reason or cause of motion, we call this branch kinematics. Kinematics. So what is kinematic? Studying motion without looking at the cause of motion. Kinematics. So you can write it down. What is kinematics? Define kinematics. Studying motion without looking at the cause of motion. Just motion, moving, object move. In this chapter, chapter 5, we start questioning. We ask the question, why the object speeds up? Why it's slowing down? Why it's changing direction? What is the cause of all these things? When you start questioning, looking for the reason behind motion, we call this branch, we call it dynamics. Dynamics. So what is dynamics? Studying motion, but taking in consideration the cause behind this motion, why the object moves. Taking in consideration the cause of motion, why it moves. Right. Let's start with a very simple question here. If you have an object in motion, and I ask you this question, what causes an object to accelerate? What causes an object to accelerate? If you have an object in motion, and this motion is not a constant, it doesn't go with a constant velocity, it changes the speed or the direction. Remember, you can have acceleration in 2 ways, or 3 ways actually. Changing the magnitude only, speeding up, slowing down. Changing the direction only, like in uniform circular motion. And changing both when you have non-uniform circular motion. These are examples. So here you have an object accelerating. Now the question is, why is accelerating? What makes an object accelerate? What do you need to accelerate? If you are driving a car at constant speed or constant velocity, how do you accelerate the car? What do you need to do? You press on the accelerator, yeah? The petrol pedal. Now, when you do that, what you are actually doing? No, that's on the pedal, applying a force. You're injecting more fuel to the engine, yeah? Okay, when you inject more fuel, it means in the chamber, between the piston and cylinder, you are burning more fuel, and the explosion will be bigger. So you're pushing the pistons up with a bigger force, yes? And then this is linked or connected to a crankshaft. Remember the crankshaft on top of the pistons? You have 4 pistons. So when the piston goes up, it turns the crankshaft. And this motion will go to the tires. So it gives you more speed, yeah? So in all that, when you press the accelerator, you injected more fuel to do what? A bigger explosion, yeah? Stronger one. So to apply a bigger force on the crankshaft, yeah? So you give a bigger torque to turn the wheel. So now you should answer the question. What causes an object to accelerate?
Energy.
Not energy. What do you need? One word. Give me one word. Force. So if you have a force applied on an object, you can change its velocity, accelerate it. But if you don't apply a force, you can't, yeah? So here we need a force. When you apply a force, you can accelerate the object. But if you don't apply a force, then there is no acceleration. There is no change in the velocity. Remember the projectile? Horizontally, how much is the acceleration? AX? 0. So how much is the force horizontally? 0. Now, what did we say? Initial velocity in x equal final velocity in x. There is no change, no acceleration. But vertically, there is V initial vertical, V final, yeah? Vy changes because there is a gravity, force. So whenever you have a force, you can generate acceleration by force. But if you don't apply a force, there is no acceleration. Now, what happens here, the famous scientist Newton, Isaac Newton, he studied the relationship between force and motion to understand dynamics, yeah? Why the object changed direction, why it's accelerate, why it's slowing down, okay? And when he studied motion with force, he came up with 3 laws. We call them Newton's laws of motion. That's why I call them laws of motion. There are 3 laws. First law, Newton's first law, and Newton's second law, and Newton's third law. So we'll go through these 3 laws one by one, yeah? We start with the first law, Newton's first law. Newton's first law. What is Newton's first law? It's a very simple law. Can I take this one? I need this. This is the pen on the table. A pen on the table, yeah? What is the status of the pen? At rest. Stationary. No motion, yes? Newton's first law says that, it's a simple, we all know it, yeah? It says object means mass. Object at rest remains at rest. This is the object at rest. It will stay at forever. This object will stay here forever at rest because it's at rest. This is the first part of the Newton's law. Object at rest remains, you can write it down if you like. Object at rest remains at rest. Now the second part. Now this time the pen, it's in my hand, and I'm moving with constant velocity. Or I throw the pen, but not under gravity. Be careful. That's the problem here because we have gravity. If you hold this pen in space, out in space, no planets, empty space except the pen and you as a ghost, because you can affect the pen as well. Your soul, not your body. Just your soul acting. And your soul holding the pen, yeah, supposedly, and you throw the pen in space this way. Okay? Which way the pen will go? Straight line, yes? No gravity, no projectile, straight. Now, once it leaves your hand or leaves the hands of the ghost with a speed or velocity this way. Now, when it leaves the hand with a velocity, the velocity of the pen will change or keep on at the same velocity. Why? Because there is no force acting on the pen. All what you did in the beginning, you gave energy to the pen to move this way, and then you are away. No effect from your body on the pen. So the pen will go forever in motion. So what is the second part of Newton's law? Object moving with constant velocity remains moving at constant velocity forever. Yes? Object moving with constant velocity remains moving with constant velocity forever. Unless, what happens? A force applied on it. When you apply a force, what you generate, so there will be a change in velocity or not? Then it changes the velocity. So what is Newton's first law? Object at rest remains at rest. Object in motion with constant velocity, not just in motion. Constant velocity remains moving at constant velocity forever unless a force applied on it, yeah? Of course, now it's obvious, but before, in the past, they thought that any object in motion, there must be a force behind it. And this is wrong. According to Newton's first law, it says no. You don't need a force to keep the pen moving. Do you need a force? If I throw this one in space, do I have to keep on a force on the pen to keep it moving? Okay. But why they believed before? Because we had gravity always. So whatever you do, it slows down, falls to the ground. Okay. An object moving, because of friction, it slows down. You throw things, slows down. Air resistance. So they thought that to keep something moving, you always need a force to feed it. This is wrong. To keep something moving forever, just remove all the forces around it. Like if you're playing hockey, ice. Okay? If you hit the ball and you have a big field, the ball, what you call it, the hockey pick. But it goes forever, yes? Of course, here, because you still have some friction, it takes longer distance to stop, yeah? But otherwise, it mustn't. So it has to go forever at constant velocity, forever. Newton's first law. Is that clear? Now, in Newton's first law, sometimes we call it the law of inertia. Law of inertia. Now, why we call it the law of inertia? What does the word inertia mean? Let's discuss the word inertia only. The word inertia means, definitions, the resistance to change of status. Inertia, we define it as resistance to change of status. Resistance to change of status. What do we mean by that? We have two possibilities for an object. Either the object is at rest or in motion. Okay? So the status is either stationary or moving. Now, inertia gives you a sense of the resistance to change of this status. Yeah? Now, if I say the pen is at rest, what's the status? At rest. Now, the inertia here means that the pen does not like to move. Will the pen move? Or it has a resistance to move? So it likes to stay at the same status. Stationary, at rest. Now look at the other way. If the pen is moving with a velocity, so what's the status? Motion. Does the pen like to stop? Or it keeps on moving forever? Why? Because it resists to change of status. This resistance, we call it inertia. Is this Newton's first law or not? Object at rest likes to stay at rest. Object in motion keeps on. It resists to slow down or change. And the one at rest, it resists to, that's called inertia. Qusur in Arabic. The word Arabic, qusur, if you want it. So this is inertia. Now, one of the laws of the universe is this. Inertia is one of the laws of nature. If I have the pen, look at the pen. The mass of the pen is big or small? Okay. Now, if the pen is at rest, of course it has inertia, yes? Resistance to move. But is it easy to move the pen or it's hard to move the pen? Easy, because the mass is small. But if I have a massive stone, big stone, at rest, it's easy to move it, set it in motion, or hard? But both of them, remember, they were at rest, yes? But it was easy to move the pen, hard to move the stone. Why? Inertia. The bigger the mass, the bigger the resistance to change of status, which means the higher the inertia. So here it means there's a relationship between mass and inertia. Mass and inertia. So you can think of it this way. Mass is a measure of inertia, or inertia is mass, directly proportional. So whenever you have a big mass, it means you have a high inertia. A small mass, a small inertia. So small objects, they have a small inertia. Big objects, big inertia. And this is one of the laws of it. Can you say why? Can you argue this? Can you say why? You can't. This is a law of the nature. This is how God created the universe. Maybe later on, God creates a new universe with a law different from this. A small object, they have high inertia. You can't argue these things. These are fundamental laws, yeah? This is how God created the universe. Small object, small inertia, big object. When I say small, I don't mean small in size. Small in mass. Small in mass, yeah? So that's why we call Newton's law of inertia, okay? We still have two more laws. What is the second one? Newton's second law, okay? But before I go to the second law, just a couple of things, because I want to leave those for the next one. The word mass and the word weight, we have to be careful about these two in physics. Weight and mass are not the same, yeah? Remember, mass measured in kilogram or gram, and weight measured in Newton. Okay, what's the difference here? When you say weight, you mean the force of gravity. And the force of gravity is constant or changes from one place to another? Okay, so if I measure your weight here, be careful. I'm not using the word weight outside the class of physics. Outside the class of physics, weight means, because when I say, what is your weight? You say 50 kilograms, 60 kilograms, yeah? But in the class of physics, wrong. When I say, what is your weight? You have to tell me, what is the force of gravity on you here? How many newtons? Force of gravity. And there's a difference. Mass is a scalar. Weight is a vector, direction. Force of gravity. So when we say weight, we mean the force of gravity, newtons. But when we say mass, we mean the mass, kilogram. Now, how you define mass? Mass is the amount of substance. Amount of substance. But weight, force of gravity. Now, if you have an amount of substance, if you have a glass of something, this glass of water, wherever you go, will it change? Or it stays the same? That's why mass is constant everywhere. You go to the moon, to Mars. The only time changes if you take from it or you add to it. But your weight, no. Because force of gravity. You are here, you have a weight. But you go a bit higher, you feel lighter. Yeah? Lighter, not your mass change, but your gravity, the gravity change on you. Okay, so I'll stop here. Next time we'll continue on Newton's second law and third law. Thank you.